this work was carried out in Lisbon, in Instituto Superior Técnico, coordinated by Professor Rita Bento, with a large team of architects and civil engineerings. It's about a Timber-Masonry-Steel building using the equivalent frame method, as Professor Pena said. And I'm going to start explaining our motivation, the case study, which is named the APPI building, the experimental dynamic characterization, then the equivalent frame modeling, the numerical results, and conclusions. So the motivation started with the complaints of vibrations felt by the users of the Association for the Protection of the Early Childhood, which is APPI, the owner of this building. This building is their museum, and on one side is their museum, and then on the other side is their offices. So they felt a lot of discomfort in the offices and in the museum due to the level of vibrations. You can see the building is very near the river in an area named Santa Apolónia in Lisbon, and a discomfort level assessment was carried out, and now I'm going to present you is the seismic assessment that came after. The building was constructed in 1901 in Santa Apolónia, and it was designed by one famous Portuguese architect, Ventura Terra. It is a building representative of the national construction of the epoch for its style and construction techniques, which makes it part of the building of the country's built cultural heritage. The case study, which I will call always APPI to be easier, it's an almost rectangular asymmetrical in plan. It's 10 by 22 meters square, with walls of more or less 4.85 meter height. To obtain the geometry and the correct characterization of the building, a laser scan was carried out. Also due to the importance of the building, which is a museum, so like this we have everything registered. The ordered point cloud was created with the laser scanner, and then a model in BIM was developed by a student, which allowed to create then the numerical model. You can see here we are entering in the BIM model. We can see that the building is one floor on this side, and then on the other side we have two floors. It is a mezzanine, and here we are passing from the point cloud to the BIM, and this is the part of the offices. So the part with the two floors. The building structure was renovated in 2014. It had to be completely rebuilt, since it was found out that the majority part of the structure was all very damaged. So the renovation kept the same exterior layout as the original. So they substituted the elements, but they kept the layout with the timber frames and the masonry walls. But then I added an alteration to the architect's design. They added a mezzanine type steel structure on the inside, as you can see here on the right side of the plan. This is the part of the offices, as we saw in this video. And then on the left side, we have just 1 story height, which is the museum part. I also show to you the 6 timber frames, because this building, in fact, is a timber building, which the main structure that carries the loads are the timber frame elements. In this, actually, this drawing is from Necrep, the company of Alexandre Costa, who just presented before. So they did the evaluation of the state of the timber elements before the renovation. And so you can see here that the building was the first part to be built in the renovation was the timber frame. So the timber frame is what carries the vertical loads. The foundations were also rebuilt. The old ones were destroyed. They built new foundations, and then the timber structure. The rooftop is also with OSB flakes, and then they started adding the masonry as an infill. So the masonry used was the same type of bricks that were before, so vertically perforated clay bricks with 12.2 centimeters thickness, and the layout was kept the same, as you can see here. Now talking about the steel part, the mezzanine. The mezzanine had independent foundations to the outside part of the structure, but then it is connected, as you can see here on the image in the detail on the right side. You can see here the connection of the mezzanine to the timber frame. So it's connected to the timber, the 6 main timber frames. The ambient vibration tests were carried out to characterize the structure, and the positions that we used to obtain the main vibration modes were the 4 points on the corners of the building. We used triaxial accelerometers with a full range of +1 G and sample frequency of 200 Hz. The results for the first vibration modes for each direction are here presented. So in the transverse direction, we call the Y direction, it's 4 Hertz more or less, and then in the X direction, which is the longitudinal one, more or less 5.05 Hertz. The building, the numerical model was built in Tramuri, of course, and this is the 3D model, as you can see. The timber elements considered are the structural maritime pine, which is the most typical type of timber to use in Lisbon. Class C18EE, so structural. These properties and this class were all retrieved from the Portuguese standard that I mentioned here. These were the values used. Then for the steel elements, we used the S275. Everything was very detailed for the steel part in the renovation works. These were the sections we used. And then the material, the masonry elements. For the masonry elements, we considered vertically perforated clay bricks with lime mortar. The values were obtained from the Italian standard, and we used also the more Coulomb laws, and with shear drift and bending drift also defined in the codes, with a confidence factor of 1.2. Then this is a very important part, the modifications of the automatic mesh. It was so the building has very particularities, as it's not a masonry building, it's a timber building with masonry parts. So some part we had to adapt to represent the real case. The first thing that I want to mention is that this part of the timber frame, you can see here this triangle. So in order to represent it, we define these horizontal elements as flexurally rigid elements with a very high inertia and plastic modulus. And then also the vertical elements that frame the window and the doors, they were not explicitly modeled. As you can see here in these images, we noted that some of them, they are not connected to the foundations, and others, you can see on the second image, they were patched. So the old part of the element, the old timber element is still here, and then a new element was patched. So these elements, the ones around the windows and the doors, they just served for it to frame the windows and the doors. But then the 6 main timber frames, as you can see here, they were modeled as they were the structural apart and were in fact new elements connected to the foundation, as you can also see here, detail of the connection. Also, modifications to the automatic mesh had to be carried out manually in order to represent our real case. So, as I said, the timber elements around the doors and the windows, they were not specifically modeled, but they were taken into account as they in fact altered the dimensions of the piers of the masonry piers. So in here, this low part, you can see below the window, I had to alter the size of the rigid notes to consider the horizontal timber beam that exists here and that separates the different masonry. So that part had to be carried out and manually introduced in all the model. Then, as the building has the mezzanine at the middle height inside, only on one side of the structure of the plan, and on the other side it's just one floor. When you add the floor, Tremuri divides the entire plan with this level, and we don't want that. So we also changed this mesh, as you can see here on the left side, and also on the transverse wall, as you can see here, an entire pier was created. So the intermediate nodes on this side were all eliminated, but then on the right side, where in fact there is the mezzanine, we keep these nodes, so we keep this level, and the piers and also the timber columns, they are divided, as the mezzanine will have an influence here, creating damage in this part. Furthermore, also there is this alteration here in the connection of the pier to the rest of the structure. So it had to be created an extra nodes in plans in order to guarantee that the masonry element was not connected to the timber column, because as it was observed in the details and in the photos of the renovation, we can conclude that the timber frame was built initially, then the masonry part was added, which means that the masonry in fact doesn't carry almost any significant load, basically just its self-weight. So in this case, we create separate nodes, and we connect these two elements with this horizontal element, which is a timber beam. As it's in reality, there is a timber beam around the top of the building, and like this, we guarantee that almost no loads from the roof are transferred here to these piers. About the loads, so again, to guarantee that the masonry walls do not carry significant vertical load besides their self-weight, instead of defining a mass to the roof elements here, we didn't define the mass of the roof elements, but we applied by concentrated loads where the roof will in fact be supported. So these concentrated nodes here. All of these aspects that I just detailed were essential to calibrate the model. Some of them we actually understood not immediately in the beginning when we started to model, but then when we started to calibrate it, we understood that, okay, the structure was built this way, so we have to make these alterations to take into account. All of these steps were very important. And like this, we could obtain a good calibration with errors of 10% to the experimental results. And we also obtain a similar deformed shapes. You can see here the first row is the frequency in the transversal direction, in the y direction. In the case of Tremuri, we can obtain some curvature in the deformed shape of the longitudinal walls, which in the experimental results we cannot see, as we only used the 4 sensors in the corners. And then the X direction, again very similar to the experimental deformed shape. You can also see here the deformed shape of the walls, the masonry walls with the timber frames, and also the metallic steel elements. About the numerical results, pushover analyses were carried out for the longitudinal X direction and the transverse Y direction of the building, using uniform and triangular loads distribution. You can see here that the triangular is the most demanding one, so that will be the one that I will detail the most. Here, looking at the horizontal direction for the triangular loads distribution, I marked the 3 points of this curve as the definition of the ultimate displacement was also an important step of this work. So the Tremuri continues the pushover curve indefinitely, as there is no limit, drift limit defined for the beam elements. So therefore, the beam elements continue to resist in this building, the timber frames, the timber pillars. The first point, the blue one, is when all the masonry piers reach the ultimate displacement. So when the masonry is collapsed, you can see here for the colors, all of them reach collapse. This would be the most conservative ultimate displacement, ultimate point. Then we can go with the curve. You see there it still has strength, and you can go until more points. The second point that I marked here is the plasticization. The plasticization of the steel beams. So you can see here, in this case, the beams on the mezzanine, on the floor, they are plasticized. And then we continue to increase the strength of the building and reach to the point where in the main facade, all the timber pillars are plasticized. So this was our limit. We could even exploit maybe even more, but this will depend on the level of knowledge that we have on the connections of the timber piers, the timber columns to the foundation. So if they are well connected, the rotation that this connection allows or not. And we don't have that information, so we stopped here at this point. Again, for the Y direction, we can observe the same points. The blue point where the masonry piers reach the ultimate displacement, then the plasticization of the steel beams, and in this case also the columns. For this direction, the steel structure suffers more plasticization, and then in more elements, and then the plasticization of all the timber pillars on the transverse facades as the last point in the curve. So just to conclude, my presentation is almost finishing, and I would just like to say that it's important to know the construction sequence and details of the structure in order to create a realistic model. This was one of the very important aspects while building the model and making sure that it was representing the real structure. As you can see, the details that I showed, the first sequence starting with timber frames, then masonry, the connections of the steel structure to the timber frame. And then, even though Tremuri is specialized in masonry structures, we can see from this work that it has the capability to model the mixed timber masonry buildings. There are limitations in the modeling, of course, of the timber steel frame buildings. We see that it's necessary to add the possibility to define the drift limits to the timber elements in Tremuri. It is also necessary, we didn't carry it out here, to make the evaluation of the connections between the timber elements and the steel elements also. It is also, while modeling this type of buildings, it might be necessary to manually alter the macro element mesh to better capture the real behavior of the structure, as I showed here with these examples. And last, the ultimate point of the pushover curve can be defined considering different limit states. For instance, a code-defined drift limit to consider that as the ultimate displacement of the curve. The failure of the masonry piers, as we showed here, a more conservative approach, or then the plasticization of the timber piers. And last, a full development of the plastic mechanism, but only if there is the confidence in the connection of the pillars to the foundation and if the rotation capacity is known. Thank you very much. My presentation is over.